Hello friends, welcome back to my YouTube channel MS Maths. In this video, we are going to discuss about measure and integration theory. That is basically some theorems and result related to the measure integration. So basically, we'll discuss a theorem that is basically prove that a constant function is measurable function. If you want to prove a constant function is a measurable function, then we will show the constant function related to some other measurable function so that we can compare. If it is measurable, then the constant function is also with a measurable function. So let's start the theorem number one. So proof of the theorem is basically let C belongs to the real number and f of x be a constant function. Okay, so it is a constant function such that f of x is nothing but constant function, then it is C for every x belonging from the real number. So let alpha belonging from real number, then there is a definition that x such that it is basically the definition of the Lebesgue measurable, or if we wish to show any function to the measurable function, then it is basically the in the form of this is basically such that f of x is greater than alpha. Now I can write this as x, okay, yeah, the set x such that f of x is nothing but c and c greater than alpha. Now, if c greater than alpha, or yeah, if c greater than alpha, it means alpha less than c, then it means it will be a real number. It will be a whole real number. But for alpha greater than c, there doesn't exist. There doesn't exist any type of set, so it will be the phi set, or it will be the null set. Okay. So in this case, we have the definition. This is the this is basically the definition. This is the definition in which if this function will satisfy this condition, or the function will occurs or arise in this set particularly, so we'll say that it is a measurable function. If alpha greater than c, then it will not be in this, it will not be in this set. So that since, so basically this is equivalent to this r and phi, since the set of real number and the empty set is a measurable set. So these both are measurable sets, then f of x is equals to c is also measurable. So it means we just compared, or we just write the constant function in terms of real number or some phi set. So this is the small, or basically short proof. Okay, next. Theorem is basically the fn be a sequence of measurable function such that fn tending to f, it means fn converging to f, then f is also measurable. So it says that if this sequence is measurable, this sequence of a measurable function, then if it is converging to a function, then that function is also a measurable function. So let's start. How can we start this theorem? So proof of this theorem is basically given. Fn is measurable. So it is a sequence of measurable functions, and it is also measurable, and Fn tending to f. So what is the definition of convergence? If it is converging to some point, it means the limit superior and limit inferior will equal. So it is basically a convergent sequence. If it is a convergent sequence, then by the definition of the convergent, the limit superior of fn will equals to the limit inferior of fn, that is nothing but limit of function fn. Now what is the limit of function fn? Is the f. The limit of function fn is basically f when f tending to infinity. So it means that it is basically the limit of function, or basically f is equivalent to the, or equal to the limit of the function, limit inferior, limit superior, and the previous videos we have described that the limit inferior and since the limit inferior of Fn and limit superior of Fn is also a measurable function. If these both are measurable, then f is also a measurable function. So the f will be a measurable function. Okay, this is the reason that the f is measurable. Now that we have a definition is basically the characteristic of a function. So what is the characteristic of function is basically let a be the subset of real number, and the characteristic of function a is denoted by chi a. Okay, then chi is defined if x is belonging from that set, which is basically a subset of R, then it is 1. And if it is not belonging from A, it means it will be 0. So this is the definition. It is also known as inductor function. Okay. So a theorem related to this is basically, yes, prove that the characteristic of A is measurable if A is measurable. So the characteristic of the function is also measurable if the function is measurable. It means the proof of this theorem is basically let A be the subset of real number be a measurable function. So if it is a measurable function, if it is a measurable function, then let alpha belonging, then alpha belonging from real number. What is the definition of a measurable function? If it is a measurable function, then it will satisfy the condition x such that function, and our function is basically chi n, or chi n of x is basically greater than c, and it is what? It is basically the chi. Now, it is equivalent to, how it is equivalent? It is equivalent to real number whenever alpha less than 0. If it is equivalent to A whenever alpha is equals to 0. It is equivalent to again A whenever alpha belonging from 1, 0 to 1, and it is phi whenever alpha greater than equal 1. Okay, since if it is equivalent to these all sets, then since real number A and phi all are measurable sets, then the characteristic of function A, which is basically the characteristic A chi x, is also pure measurable, because we have proved that this is equivalent to all these things. Okay, so it is also with a measurable set. Whenever if it is basically it is equivalent to all these sets, then it is possible. So it is all about the characteristic of the theorem and the two important theorem, or the short theorem, or like very simple theorem, and the proof is very simple. I hope you are getting the point. Thanks for watching my video. Keep watching MS Maths. For more videos, you can subscribe my channel, share the video, like the video. Thank you. Bye bye.